All right, so we're summing over n.
I see a lot of naked ladies when I looked at Being Not Filtered.
Yeah? I expect you may have.
Probably a lot of low-pass filters going on. Nothing related to filters.
All right. Let's get our game face on. Okay, so this is just a sum, right? So it's going to be, and all of my x of n's are 1 in this case. I couldn't have made it a whole lot easier for you. So really it's just e to the j omega plus e to the j omega 0 plus e to the minus j omega. These guys give you 2 cosine omega, and this guy gives you 1. Okay, so yeah, but the n is -1, right? So this is, it's minus -1 and minus plus 1.
Cosine omega n.
No, there's no n. Where's the n? Is there n in here? I'm done with n.
He said 2 cosine omega n.
Oh, I said n?
No, he said 2 cosine.
Yeah, but there's no n. There's no n. This is just e to the j omega and e to the minus j omega.
You couldn't have any n's, but that would be samples.
I've already substituted in my n's. N was 1, so it's gone now.
Yeah, it's a domain switch.
Yeah. There's no n's anymore. Like, it's just that. If I had more samples, like if I gave you this function, right, then you'd have another term which was 2 cosine 2 omega, right, because this would be e to the minus, sorry, this would be e to the j2 and e to the minus j2, and that would sum to give you 2 omega rather. This would give you e to the j2 omega, and this would give you e to the minus j2 omega, and you'd sum them and get that term. But that's it. Like there's no n. So you get this. Is this a what's the one property we should always two properties we should always expect for our Fourier transforms and the frequency in discrete time? Periodic with what period? Just 2 pi.
Just 2 pi, yeah.
In the discrete frequency. So is this signal periodic with period 2 pi? How can I tell? For any cosine, what's the period?
2 pi over.
Right. Any cosine, right? Just the base cosine has frequency 2 pi. Well, there you go. 2 pi. That's good.
2 pi over negative.
Right. So now I think this marker's done. So now I go to plot it. So it's 2 cosine plus 1. So let's just do this in steps. If it was 2 cosine, it would look like that. Okay. If it was 2 cosine plus 1, this would be like that, and this would be, that would go from I just add 1 to both terms. Okay. And now I got to take the absolute value of it. All right. So how do I take the absolute value of it? Okay, so there's your butt cheeks. So putting it all together, we get
Just drop the right. You wanted the whole thing?
well, I'm just it's infinite, right? I could just keep going on and on, right?
Wait, the one on the right
Plus
is...
1 would be over the entire thing, right?
Isn't the one on the right the final?
Yeah, the one on the right is that was my scratch paper. I'm just cleaning it up here. What's the question?
Wouldn't it be from 3 to 1? In the
No. No. It was cosine goes from -1 to 1. I double it, now it goes from -2 to 2.
Oh,
And then I add it, it goes from, instead of -2 to 2, I just shift it up. So -1 to 3.
I'm sorry.
It's fine. I'll hold it against you. Okay. So what's this frequency? What's this frequency? Let's say easy. What's this one? 0. Good.
Oh, that's 2 pi.
4 pi over 3.
You still got to extend it.
That's 4 pi over 3.
Bring it up.
2 pi.
Oh, this is okay. This turns out to be a good question. Okay.
I know.
Yes.
Pi with you have to like.
I'll give you a hint. No one said the right answer yet.
You have to use
Where's 2 pi?
it's at the middle.
I'll give you a hint. The signal is periodic with period 2 pi.
Over 2.
It's at the middle right there. Middle of the big peak.
Middle of the big peak is what? 2 pi! I have the marker. I'm the winner. Okay, it's periodic. It repeats itself every 2 pi. So if this is centered at 0, this is at 2 pi, this is at 4 pi. 6 pi, blah, blah, blah. So where is this? Pi, thank you. Okay. I didn't ask you for this, but what's that? I didn't ask you for that on the quiz. Is it really? I don't know.
Nah, I think that
It's where this equation equals 0. Right? So by inspection, I can see that this is going to be omega equals inverse cosine of -1/2. What? What?
I don't think that equation equals 0 at pi, though.
No, it's not. Oh. Oh, crap, you're right. Damn. Oh, is that why you're confused?
You only want one tiny bump.
Yeah, all right. I concede. Okay, I was a loudmouth ass for no reason. Okay. Yes, now we're cooking. Okay, I beg your pardon. Now you happy now?
yes.
I'm sorry. Okay. Good. And that's 3, and that's 1. The height. Okay? So this is a low frequency signal or a high frequency signal?
Low.
Mostly a low frequency signal, right? And that's sort of what we'd expect because, the signal's not changing, right? It's basically low frequency. The only place it's changing is at the edges where it goes from 0 up to 1, right? So we sort of expect a sinc function, and that's basically what's going to pass for a sinc function in this game. Pretty spiffy, eh? We try. Okay, so let's talk about how we will actually build this filter out of stuff. Okay, you know how to build analog filters out of stuff, right? You go to your box and you get out an op amp and you get out some resistors and capacitors and wire and you connect them together, right? So we know how to do that. But what about a digital filter, right? I mean, you ain't going to use a capacitor to make this, are you? So here's how it works. Let's start with signal x of n. Okay. Now we are going to take signal x of n, and we're going to do the following to it. We are going to pass it through. We're going to call this B sub. I always get this wrong. I feel like such a ditz. Okay, let's call this B sub 0. I'm sure this is not the standard notation, but whatever. Okay, this is a multiplier. Can we multiply discrete numbers together? Totally. You guys have taken digital, haven't you? You know how to add, 2's complement numbers, how to multiply 2's complement numbers. I mean, you could actually make a circuit to multiply 2 numbers. So that's what's going on here. So this is saying take the current sample of x of n and multiply it by some constant, right? A constant which I'm going to provide to you. All right. And here we're going to put a summer block. Okay? We know how to make summers, right? I mean, in digital, you learn how to multiply numbers, how to add numbers. Okay, well, here's a multiplier. Here's an adder. Now, we're going to add one more piece to the puzzle. And that piece of the puzzle is a box with a D in it. Any takers on that? Sort of. What's the discrete time equivalent of a differentiator? No, it's a delay element. We'll do an example of this in a second. All right, let's do one more layer. We can do as many layers of this as we need, but we'll just do one. We'll do 3 layers. All right, you with me? So, let's say we have some signal x. All right, so x has got a bunch of numbers in it, like a bunch of samples. 1, 3, -4, 7, 2, 6, and so on. All right. So just for kicks, somebody tell me, this 7 is x of what? 0, 1, 2. I like to start numbering at 0. Okay, so this is x of 0, x of 1, x of 2. That's x of 3. Okay, so here's how you play this game. So right now, all I've done is I've delved into my digital toolbox, and all I've pulled out is multipliers and adders and delay elements. What's a delay element?
Just holds it for one clock.
Yeah, it's basically like a flip-flop, right? Or yeah, like a D flip-flop. Or like a buffer. So here's what we're going to do. So let's say this filter's been running for a while, okay? So let's say what I have here is x of 3. So is this how I want to explain this? Actually, you know what? I'm going to keep this generic. Let me just take out that x of 3. We'll get back to the x of 3 in a second. If this is the nth sample of x, what goes here?
N plus 1.
And minus 1?
The previous sample of x. Right? So basically what you're going to do is your current sample goes here, and then after you're done with the current calculation, you're going to take that current sample and bump it back 1. Okay, so you can take that current sample and put it here. And then again, and then after the next calculation, you bump it down once more. So if this is the nth sample, this is the previous sample. This is the x of n minus 1th sample. And this is the x of n minus 2th sample. N minus 2nd? I like tooth better. It sounds less sophisticated. All right? Okay, so let's put this together. What does y of n equal? Well, let's work it. If this is x of n, and this is the multiplier b, what number do I have here? Good. I have b0 times x of n. Okay. Now, that's not all that goes into y. Some other stuff that goes into y is this branch. Okay. Well, what is that branch?
So it'll be plus x of n minus 1 times b.
You kind of get the hint here. So it's b1 x of n minus 1 plus b2 x of n minus 2.
Here, this looks like it's going to result in very high numbers coming out.
So
Depends on your values of b.
will it converge to b sub n times x of 0?
How do you mean will it converge?
If you were to add n amount of delay elements, would the last sum, would the last thing to be summed be b sub n times x of 0?
No, this is b sub n minus. Right, the last thing would be b sub n times x of. Oh, we can't use n. Crap. What do we do? There's another subscript. I think it's m that we use. So it's x of n minus m. Just however many coefficients you have, you just keep going. Okay. Now, let's actually run an example of this. All right. So let's say this is our x of n. What do you want to use for your filter? So if it's not immediately apparent, the coefficients b0, b1, and b2, that's your filter. So for example, on the quiz today, you had that. That's your b0, b1, and b2. Okay. Now, just to make this a little interesting, let's diverge a little bit from what we did on the quiz, just so we don't have ones everywhere. Let's say that our filter is 1, 2, 1. And I don't care, like, it's really irrelevant where n equals 0, n equals 1, and n equals 2. Like, I don't really care about the n values, right? It's just, that's my filter. Okay? So, for this example, we're going to say that b of 0 equals 1, b of 1 equals 2, and b of 2 equals 1. So, starting from there. Is that right? Let's see, x of n. Yeah, I think that's right. Okay. So, let's actually go and do the convolution, right? Let's just actually work the steps. So, let's start with n equals 0. Okay, so n x of n, y of n. So let's start at n equals 0, shall we? Okay, so I'm actually just going to write the numbers in here. So what goes here? X of 0, right? And what is x of 0? 1. What's this? Okay, so now these multipliers are always going to be the same, right? They're not going to change. So this is going to be times 1, times 2, times 1. Okay. Now, what's this number going to equal?
0?
Right, here it's a little bit tricky, right? This is the very first sample. So what's before the first sample?
Unknown?
It's unknown, and usually you slap in what's called an initial condition. In MATLAB, it'll actually even let you, you're not really even obliged to put in, to seed it with zeros, but people usually do it. It's like your initial condition. So I'm just going to seed both of those with zeros for the time being. I'm just going to pretend that there are two unknown zeros that, before my signal started. I think I decided I lied. This is the B0 term over here. That's B0. Sorry. Okay, good. So x of n is 1. So what's y of n? Right, it's 1 times 1 plus 0 times 2 plus 0 times 1. Yes?
So we're neglecting that it's got to clock up to the y then?
Yeah, we're not neglecting it. It's just that's how it works.
Okay. Well, there would be a delay between x of n and y of n, wouldn't there? Because it needs to go through a multiplier and then an adder?
Well, no, this is
No, you wait. Like what you do is like you present, at this moment in time, this number is available, this number is available, this number is available. You wait till the multiply and the add is complete. So you have to make sure that whatever your clock time is long enough to accommodate a multiply and an add. Yes.
So is this basically like a numerical analysis of a convolution?
Yeah. Right.
So that's why you start with 0 usually?
Sure. Basically what we're doing is convolution. Right? And that'll become apparent as we actually work this, right? Okay, so we said y of 0 is 1. Okay, now let's iterate. So now I clock the system. So now it's n equals, now I'm working with n equals 1. So what's x? So let's see. So everything gets delayed. So this 0 goes down to here. That's easy. This 1 goes down to the delay pipe. That goes to here. And what goes up here? Right, x of 1, 3. Okay, so now it's 3 times 1 plus 2 times 1. So what do we get? 5? And we can play this game all day long, right? It just goes on and on and on. Let's do one more. Okay, on the next time step, what goes down here? Right, so the one hiccups down. The 3 hiccups down. And now I'm left with a minus 4. So minus 4 plus 6 is 2, plus 1 is 3. So 2 minus 4, 3. And it goes on and on and on. Okay? And as many data samples as I have in X, I can get for Y. Right? It just keeps going. Now, really all I'm doing is a convolution. Right? Because look what I did. I took this, what you can do is think about, like I've taken this signal, I had my filter, which is like that. Remember convolution, you take one of your signals, you flip it, and you shift it. So let me take my signal and flip it. 1, 3, minus 4, 7, 2, 6.
Quick question.
Yes, sir.
When we do a filter, shouldn't we also see the negative magnitude so we can see if it actually amplifies or reduces it?
That's a frequency domain argument, and we can look at this in the frequency domain. But right now I'm doing a time domain analysis. It's like, I mean, it's the same thing as continuous time systems, right? We can either convolve two time signals together, or we can take the Fourier transform of the impulse response and look at the transfer function and determine if there's a gain or not. But I'm not doing that in this case. I'm just doing a time convolution. I don't know, does that answer the question? Maybe not. Well, okay, that's fine. No, I mean,
No, my question was, like, I was thinking about the quiz, right?
Yeah.
The filter. Like, does it really amplify everything? Because we don't see what happens. Like, if it, no, never mind. I'm thinking about with the clock. That's right.
no, it's a good question. So the filter the filter in the quiz did have a gain, right? If the filter in the quiz, that's actually a good question. The filter in the quiz was 1, 1, 1, wasn't it? And what did we find was the gain at omega equals 0? 3. The gain at omega equals 0 was 3. So that implies that if I take a DC, a signal with frequency of omega equals 0 and pass it through this, it'll get gained by 3. And that's exactly what would happen, right? So we said that the magnitude of h of omega equals 0 for the one on the quiz was 3. Is that right? Yeah. Okay. So that means that if I create a signal, if I create cosine of omega n where omega equals 0 and filter it with this filter, the signal that I'm going to get out should be the same as the one that went in but 3 times bigger. Okay. So what does it look like when it's for cosine of 0n? What does that signal look like? Cosine of, no, just the input signal. Cosine of 0n. What? It's a constant, right? It's a DC signal. So a bunch of 1s. So do the convolution now. 1 times 1 plus 1 times 1 plus 1 times 1 is 3. Okay? Shift it again. 1 times 1, 1 times 1, 1 times 1, 3. So in this manner, the signal that will come out will be, instead of your input signal was a constant stream of 1s, your output signal is a constant stream of 3. So in that case, there's a gain. What's complicated here is that your input signal isn't like a single frequency. It's a whole bunch, it's a whole mess of frequencies mushed together. So look, we're doing convolution, right? I took my input signal, I flipped it, and now I'm just going to multiply and add. I've got 1 times 1 is 1. I'm done with the first sample. Now I shift it. Now it's 1 times 3 plus 2 times 1. 5. Shift again. 1 times negative 4, 2 times 3, 1 times 1, 3. So we're just doing a convolution. All right, now. Let's see, how am I going to explain the last bit here? So what I want to get out of this is the following. I'm trying to draw some analyses, like some comparisons here. So Whereas for a continuous time signal, I showed you a circuit. For a discrete time signal, I'm showing you this. Okay, so this is sort of like, this matches the circuit. What is this the equivalent of? What part of the continuous time analysis does this equation match? Transfer function is in the frequency domain, my friends.
Fourier transform.
Not the Fourier transform.
Discrete time. Fourier transform.
That's the result of the time signal, I guess.
That's just your output.
No, this is no Fourier here. This is just in time. This is a complete description of the circuit in the time domain.
Oh, the differential equation.
Right. In a circuit, what is the equation that is a complete description of the circuit in the time domain? It's the differential equation. So this is sort of like the discrete time version of a differential equation. In fact, it's called, you're not going to believe this, the difference equation. Right? If you think about a differential equation, it was some constant times the first derivative, some constant times the second derivative. Well, you've got some constant times the previous value, some constant times the value before that. That's the difference equation. Okay, now, last piece of the puzzle. Not last piece, but next piece of the puzzle. What is the impulse response of this circuit, of this filter?
Would be one. Would be 0 times another impulse plus V1 times 1 plus V2 times 1.
So close. How could I find out? If I didn't know, how could I just figure it out?
Put it in impulse.
Put in an impulse. Good. So, okay, is this an impulse? No. So tell me how to write a discrete time impulse. A 1, and then what else? Yeah. A discrete time impulse is a 1 with a bunch of zeros around it, right? Isn't that an impulse? Cool. Let's try that. Let's actually take an impulse and pop it into this system, and then surely what will come out will be the impulse response, right? I mean, that's how you define an impulse response. So let's try that. So we'll start our signal here. Okay, so the first thing we'll put in is a 1. Okay, and then this is a 0 and this is a 0, right? Because we always put our back samples at 0. Okay, so what's the first sample of my impulse response? 1. Okay, now, good. So now we're done with the first sample. So this 1 hops down here. Right, so delay the 1. The 0 that was here delays down here. And what goes up here?
0.
0. Good. That 0 is that one. Okay, what's the next thing out of my filter? It's 0 times 1, 1 times 2, 0 times 1. So now I'm getting a 2. Okay. Delay everything again. So that 1 comes down here. That 0 comes down here. And then this 0 appears up here. And now what am I going to get out? I'm going to get a 1. Okay. And now delay everything again. From here on out, it's zeros. So, there's your impulse response. There's your h of n. It's the actual filter coefficients, right? Which is really easy. I mean, discrete time kind of cleans up a lot of nonsense for you. So, discrete time filters let you do something that is totally impossible in continuous time circuits. Every continuous time circuit we looked at, the impulse response had one property, and that is it was infinite duration. Right? You remember when we looked at the low-pass filter? Anybody remember what the low-pass filter step response looked like? Impulse response looked like? Yeah, there's a peak and then a decay. How long does that tail go on for?
Infinite.
All the way to the ocean, right? I mean, it's infinite. Every continuous time signal has an infinite tail on it. How about in the discrete time domain? Is that the case? No, sir. Look at this. This is what we call an FIR filter. Finite impulse response. There are two main flavors of filters, right? There are infinite impulse response, which we can talk about, and there are finite impulse response. Okay, but that's in the continuous time domain, you can't have an FIR filter. You can only have them in a discrete time domain. But it is, in fact, a finite impulse response filter, right? If you give it an impulse, after 3 samples, you're done, right? Whereas in the continuous time domain, I mean, technically speaking, if you don't integrate that thing to infinity, you don't get the right answer. Again, there's pros and cons to it, but one nice thing about it is it's quite simple, right? It's very easy to implement.
Are these now is one digital and then one's analog, or are they both digital?
You can make a digital IIR filter. Okay, and I will I've about 5 minutes left. I'm going to tease the answer to you. Let's talk about how you can make, so we've got a difference equation, and we've got the circuit build. So let me just at least give you a hint about how you can build a discrete time IIR filter. All right? What's that?
Backfeed it?
Yes, backfeed it. That's exactly right. So again, a few ways of doing it, and I'm almost certainly going to screw this up. All right, let me see if I can get it right on the first try. So there's x of n. So probably the easiest way of doing this would be, you'd think I would remember how to do this. No, hold on. Just give me a second here. I'm basically doing this from memory because I didn't prepare this before I came. Doesn't look right, does it? Oh, I'm so close. Yeah. I think it goes like this. There we go. So, the idea is that if in addition to delaying the input, you also include delayed copies of the output, then you can get an infinite impulse response because you're always feeding your output back into the signal. So it's like you're always, the memory of the output goes back infinitely long. And I think what we'll do on Monday is we'll actually run an example of an IIR filter. Because this is just sort of a diagram that doesn't make a whole lot of sense. But I think we'll actually run an example and demonstrate that you can build a Chebyshev filter or whatever that goes on forever and ever and ever. So I won't be here on Monday. John will be, but John will have the full instructions on kind of what to do. In preparation for, you are going to have recitation next week. I believe we'll be doing discrete time convolution. So come to recitation. I'll make sure that gets posted today. Any questions? All right.
So what's the test that you were talking about for every day that you do